Newton's law of gravity. I'm dedicating this lecture to Helen Cheng, who gave me the idea of using this nice white paper instead of the lined paper that was kind of annoying. So I agree with you, Helen. This is much better. So anyway, let's talk about Newton's law of gravity. Okay, so Newton was this guy who, came up with all these laws, and we've studied his laws of motion, his first and second and third law of motion. And then he turned his brilliant mind into solving the problem of why, if this is the Earth, and this is the moon, this is about the right scale, they probably should be a little further apart. Why does, look, here's the moon, and it's moving with a certain velocity. Now, the moon has mass, and it's moving, it has inertia. And according to Newton's first law, something that's moving doesn't change the way it's moving unless acted upon by an outside force. Now, we all know that the moon orbits the Earth. It moves in a curved path. And so he reasoned there must be some force acting on the moon that makes it orbit the Earth. And then he speculated that, and he was on an almond it was on an apple orchard, and there's this legend that an apple fell from a tree and struck Newton on the head, and Newton said, Eureka! It's the force of gravity that keeps, that pulls the apple from the tree, that also holds the moon in its orbit. Now, I think that's a legend, but look, it was an observation. Things fall to the ground, and he, because of his laws, reasoned there had to be some force, this force of gravity. And he's the first person that we know of that said, look, if you're here on the Earth's surface and you drop an object and it falls to the ground, it's the same force that holds the moon in its orbit around the Earth. He's, as far as I know, the first person who took something of an earthly nature and expanded it into understanding the heavens, the things up in the sky. So it was a big deal, a great breakthrough. And so what we want to do is learn about this breakthrough, learn about his law of gravity, and use it to solve problems. This is one of my favorite subjects to teach throughout the whole year. It's really astrophysics, so it's very cool stuff. Now, we're going to call this the force of gravity, and that is the Earth pulls on the moon, but the moon also pulls with an equal and opposite force on the Earth. They pull on each other, and actually the Earth-Moon system orbits around the center of mass of the system, which is, believe it's like inside the Earth. The Earth actually wobbles as it goes, as the moon pulls it, and as the Earth moves in its orbit around the sun, it actually wobbles a little bit because of the pull of the moon. But if you were just looking at it, if you were above the Earth-Moon system and looking down, and you waited long enough, about 29 days or so, it would really look like the moon is just in orbit. If this was the Earth and this was the moon, it really would look like it's moving in orbit around the Earth. And it is. So, now here's what he said. Here's what he reasoned, and we're kind of cutting to the chase here. It took him weeks to do this, and we're going to do it, in a few minutes. But he said, look, the Earth has mass. Let's call that M1. The moon has mass. We'll call that M2. And so you have two massive objects, and they apply an attractive force to each other. And the amount of force depends on the amount of mass. If I double the masses, I double the force. If I double M1, I double the force of gravity. If I double M2, I double the force of gravity. If I double both of them, I quadruple the force of gravity. So he said, in other words, it's directly proportional to the two masses. Then that kind of makes sense, right? If you're holding an object in your hand, and then you hold two objects in your hand. Where's my other pencil? Oh, that doesn't work. But if you hold, twice as much stuff, twice as much mass, you feel twice as much weight, twice as much force of gravity. Easy to understand. But here's something that it might be a little unusual. Look, from the center of the Earth to the center of the moon, we're going to call that distance r. And it does make sense, doesn't it, that the farther apart that you make things, the weaker the force. That is, they're inversely related. If I increase the radius, I decrease the force. And he thought so, yeah, r. But it's not just r. If the moon was, let's say the moon was right here, and then I pull it away from the Earth and made it twice as far away, if it's twice as far away, I only have 1/4 the amount of force. And that's because the force of gravity is inversely proportional to the square of the distance between them. If I have two objects and I measure the force of gravity, and if I make them twice as far apart, it's 1/4 as much force. If I make them 3 times as far apart, it's only going to be 1/9, and 4 times as far apart, only 1/16 as strong. So gravity decreases by the square of the distance, and that's expressed by this equation here. Now these are the only things you can vary. You can only vary the masses and the distance between those masses. I mean, think, there's really not much else you can do. But what units does the force of gravity have? Newtons. What units do I have here? Kilograms times kilograms. So I've got kilograms squared, and r squared is meters squared. Kilograms squared per meter squared is not a Newton. Okay, so what we need to do is multiply this by something. I'm just going to call it big G, by some constant. Now, this big G, as opposed to little g. Little g is the acceleration of gravity. Okay, but which at the Earth's surface is 9.8 meters per second squared. But if you are, but big G, no, I'm sorry, big G is something completely different than little g. Big G tells us how strong gravity is. It's the universal gravitational constant. It's a constant. Now, you've dealt with constants of nature before. Think about this. An electron. What's the mass of an electron? Well, I don't remember what it is. We can look it up. But it's a constant. All electrons have exactly the same amount of mass. All protons have exactly the same amount of mass. All protons are identical to other protons. Same is true with neutrons. The charge on the electron is exactly the same as every other electron. And you find an electron, figure out what its charge is. It's the same as every other electron. So the charge on an electron, the mass of an electron, these are constants of nature. Well, here's a constant of nature. This is a little bit different. It has a value. Let's go over what its value is here. It's G is equal to 6.67 times 10 to the negative 11. Now, what units do we want? Well, force of gravity is measured in newtons. But what do we have to do? We have to cancel out these meters squared. So Newton. So we put a meter squared, and then we have to cancel out this kilogram squared. So there's our units. Newton meter squared per kilogram squared. Because when I multiply it in here, I get newtons after they all cancel out. Isn't that clever? And look how tiny this number is. This is a tiny number. It takes a lot of writing, but it's a tiny 10 to the negative 11. We'll talk about how tiny that is in just a minute. Okay, so now Newton did not know what this number was, but a guy named Cavendish, 100 years or so later, figured it out with a brilliant experiment, which we'll talk about. Now, okay, so now the force of gravity, it's a vector, so we need some way of describing the direction. It's an attractive force. if you have two objects that are attracted to each other, we give it the negative r hat direction. Negative r hat means towards the center. Now think about this. If you're looking, here's the Earth, and we're looking at the moon. Now let me put the moon a little bit closer. So here's the orbit of the moon around the Earth. It's always pulled towards the center of the Earth, right? That force of gravity is always in. Now r hat, positive r hat, what does positive r hat mean? I mean, we've dealt with that before. Means away from the center. Positive r hat means away from the center. So negative r hat means towards the center. So we give the force of gravity a negative r hat direction. It's just a way of saying it's an attractive force. No big deal. Okay. So, now, this is Newton's law of gravity. This equation right here describes gravity very well. And it was the accepted theory of gravity for a couple hundred years. And then in 1915, along came Albert Einstein, who published his theory of gravity called general relativity. And general relativity, the good old Einstein, is now considered the ultimate accepted theory of gravity. It predicts things and describes nature a little bit better than Newton's law of gravity. Now, we don't study general relativity in a freshman level physics course because this stuff is hard. The mathematics that you need to study general relativity, it's tensor calculus and other stuff that I barely remember. It's tough. This is one of the hardest things there is to study in physics. Very, very complicated. But it's accurate. But so why do we use this? Why do we still teach Newton's law of gravity if it's no longer considered the ultimate theory of gravity? Well, I'll tell you why. Because it works. It works really well at predicting how the moon moves around the Earth. If you were going to launch a spacecraft and you want to get it to Mars, you can use Newton's law of gravity and do just fine. So it's also very accessible. I mean, with a trig-based education, you can do a lot of very useful physics with this very simple, elegant little expression. So we still teach it because it's still useful. Remember, but this is really Newton's law of gravity is an approximation of general relativity. If you make some simplifying assumptions in general relativity, you end up with Newton's law of gravity. So it still works. It works pretty good. So we're going to learn it. Okay. Now I want to tell you something about gravity. It is weak. It's a very, very weak force. Now let me show you how weak it is. And if I was in class right now, I would actually do this. But let's imagine I've got one of my 1 kilogram masses here. Okay, here's a 1 kilogram mass, and I'm going to get another 1 kilogram mass like this, and I'm going to put them 1 meter apart. In fact, I'm going to put a meter stick between them, right, just to prove it. Here's a meter stick. And now, according to Newton's law of gravity, all massive objects apply forces, equal and opposite forces of gravity to each other, and they are actually trying to bring each other together. Well, what would this force be? What would the force of attraction between these two massive objects be? Let's figure it out using Newton's law of gravity. Well, the force of gravity is big G, which is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared, times the mass of this object, but it's a 1 kilogram mass, times the mass of the other object, and it's a 1 kilogram mass, divided by the distance between their centers, which is 1 meter. And then we have to square that because it's over r squared, and r here is 1 meter. Now I picked these numbers because the math is really easy, isn't it? So I get the force of gravity is equal to 6.67 times 10 to the negative 11. And look, the kilograms cancels. Ooh, it should be kilogram squared. Kilogram cancels kilogram squared. Meter squared cancels the meter squared. I'm left with newtons. That's a tiny force. Let me rewrite it a little bit. I'm going to go 66.7. I'm just going to move the decimal over 1 and then divide by 10 here, and so that's 10 to the negative 12 newtons. Now, why did I make it negative 12? Because what is negative 12? It's a trillionth. This is 66.7, or about 67 trillionths of a newton. Okay, if a snowflake were to land on your hand, the weight of that snowflake would be devastating compared to the force of attraction between these two massive objects. Now look, all massive objects are attracted to each other. Okay, tomorrow when you're sitting in class, look at the person next to you. You're attracted to them. You're gravitationally attracted to them, but you don't feel it, do you? Now, if you're feeling some kind of attraction, that's probably a subject for a biology class or a psychology class or something. You're not feeling the gravity, because the gravity is measured in the billion. Well, if it's two people, it's probably in the billionths of a newton, which is just not noticeable by you compared to all the other forces that are acting on you. Okay, so it's a very, very weak force. Now, of course, if you have a whole planet of mass beneath your feet, works pretty good. Okay, now I want to show you something. This is done very nicely in the book, but I think it's one of the coolest things that Newton did. And he figured out how massive, he figured out that his law of gravity was probably right. I need some more paper. Hold on. No, I'm good. And here's what he did. He said, first let's take a look at the law of gravity. The force of gravity is equal to G m1 m2 over d squared, or r squared. Regular physics, we call it d. And here we're going to call it r squared. And okay, let's say Newton didn't know what this was. Well, let's figure out what it is. Let's do the math. G is equal to the force of gravity multiplied by r squared and divide by the two masses, right? Okay, so all we got to do to figure out what G is take two known masses, measure the distance apart, between them, and measure the attractive force of gravity. That's all you got to do, and from that you'll get G. Turns out to be, because the force of gravity is so incredibly weak, this is a hard experiment to do, and Newton could not do it, and therefore he did not know what the value of G was. But Newton was a very, very, very clever man, and so here's what he did. So here's the surface of the Earth, and way up there is the moon. Okay, so here's the moon, and here's the Earth. Now, here's an apple, okay? If you drop an apple, it accelerates to the ground, right? And that was something that he could measure. Galileo did these kinds of experiments and so on, and he said, hey, the acceleration here is 9.8 meters per second squared. He goes, I wonder what this acceleration is and how it compares to this. Well, here's what he did now. He said, look, this object is not, this apple, how far away from the center of the Earth is it? Well, they knew what the radius of the Earth was by this time. So here's a radius of the Earth. And he said, look, the acceleration is proportional to 1 over the radius squared. So, and the moon is accelerating towards the Earth, right? It's moving in a circle, so it's got a centripetal acceleration. And so what he did is he compared this acceleration to this acceleration. And then he compared it to what you should get if you do this. Acceleration of the moon over the, this is acceleration of the moon towards the Earth, divided by g, the acceleration of gravity. Now what he said was that these accelerations, because the force of gravity is proportional to 1 over the distance squared, the acceleration is proportional 1 over the distance squared, 1 over r squared. And so he said, well, so this should be 1 over the distance to the moon, well, not the radius of the moon, but from the center of the Earth all the way out into space to the moon. The radius of the moon, I'm drawing this in kind of a perspective, but this is from the center of the Earth out to the moon. It should be 1 over the radius, and I'm going to use little r because I don't want you to think it's the radius of the moon. It's the radius of the orbit of the moon. So here's the Earth, here's the moon. I'm talking about r sub m here. That's what the distance I'm talking about. 1 over rm squared divided by, the acceleration of gravity should be equal to 1 over the radius of, how far is this from the center of the Earth? Well, it's an insignificant height above the surface here compared to the radius of the Earth. It's the radius of the Earth squared. And so the ratio of these accelerations should be the radius of the Earth squared divided by the radius to the moon, from the center of the Earth to the center of the moon squared. Well, they knew what these distances were. They knew what these measurements were. I'll just write them out for you. It's 6.37 times 10 to the 6 meters divided by, turns out that the moon is 3.84 times 10 to the 8 meters. Quite a ways out there. But this gets squared. And this gets squared. And when you take that ratio, you get this tiny little ratio, 2.75 times 10 to the negative 4. Okay, that's the ratio of the acceleration of the acceleration of the moon should be compared to the acceleration at the Earth's surface, if the inverse square law is correct. Okay, this is in your this is explained in your book on page 391. Now, then he said, well, what is this ratio? Well, we know what g is, right? G is 9.8 meters per second squared. But what's the acceleration of the moon? Well, it's v squared over r, where this is the radius of the orbit of the moon around the Earth. Okay. That's the centripetal acceleration, right? And what is v? V is, well, you go 2 pi r over the period. Okay, and when you do that ratio, you get an answer, and they did it a slightly different way. That's okay. You get a certain ratio, and okay, I'll do it the way the book did it. So they took this and they said, well, what is the acceleration of the moon? The acceleration of the moon towards the Earth, the centripetal acceleration, should be 2.75 times 10 to the negative 4 times 9.8 meters per second squared. And so you get what it ought to be, which is 2.7. And you don't have to crank through this math unless you want to, the arithmetic, times 10 to the, negative 3 meters per second squared. Okay, very kind of a tiny acceleration, but the moon's far away. Okay, now, what happens when you actually figure out what this centripetal acceleration is? Well, you go 2 pi r over the period. You square that and divide it by r. Okay. Now, what is the period of the moon around the Earth? It's 29 days, roughly 29 days, and in seconds it's 2.36 times 10 to the 6 seconds. Okay, you plug in the radius and all this, and guess what you get? You can go in the book and find these values and plug them in, and what you'll see is you'll get 2.72 times 10 to the negative 3 meters per second squared. So look, that agrees with this, doesn't it? Or it's very, very close. How come they're not exactly the same? Because the moon does not move around the Earth in a perfect circle. It's slightly elliptical. So these answers are not quite exactly accurate, but they're really close. And Newton knew that the inverse square law was good. That is, you can take the ratio of the squares of the radii, the distances r, and use that to predict the acceleration of the moon. And when you compare it to the centripetal acceleration, you get the same value. So, okay, maybe I spent too much time on that, but it's very exciting when Newton, not knowing what the universal gravitational constant was, could still prove that, or could confirm that his theory of gravity was giving a very, very accurate answer of what the acceleration of the moon should be. So it was great stuff, and one of the great achievements in the history of physics. Okay, one last thing. We talked about this guy right here, the gravitational constant equals the force of gravity times r squared over m1 and m2. Okay, so Newton didn't know how to do this experiment, but a guy named Cavendish, Henry Cavendish, in 1798 figured out how to do this. And what I think is one of the most amazing experiments in the history of, I mean, when we think about how delicate this was, it's truly amazing. What he needed to do is take two known masses, somehow figure out what the force of gravity was, and measure their distances. And here's how he did it. So imagine you have, here's the ceiling, and you take a long, skinny piece of wire. And at the end of that wire, you put a very light rod, and then at the end you put these little brass spheres or some kind of metal spheres. So this is insignificant compared to the mass of these guys. Okay? Well, then what he did is he put a mirror on the wire here. So here's like a little glass mirror. And then he allowed a beam of light. Now, they didn't have lasers in those days, but just a beam, very bright light, and had a little slit that the beam of light could come through. And he shined it onto the mirror, bounced off the mirror, and landed on a screen of some kind. And he measured the position of that. Then what he did, and so we'll call this M1, and this is M1. Then what he did is he put these big brass spheres. I want to call them spheres because I don't want to make anybody giggle. All right, so I put these big brass spheres on either side of these things at a known distance apart. And here's what happens. There's a little bit of gravity. There's a gravitational force. Now, it's very, very, very tiny, but this thing is on a long, skinny wire, and they had to encase this in some kind of big glass case or something so that air currents or nothing could interfere with it. And what it did is it gave a little tiny torque, and it twisted these. It twisted it a little bit. And when it twisted a little bit, it twisted the mirror. And now the light beam landed on a different spot. And he therefore could figure out what this angle was. And if you know the length and properties of the wire, you can figure out how much torque it took to rotate that wire. And if you know how much torque it took, and you know this distance and this, you can figure out what this force is. And so what he did is he went through a whole series of calculations. He measured the force of gravity between two known masses. It was an absolutely brilliant experiment. And he came up with 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Now, I think his answer was something like 7. I mean, it was very rough. This is a very rough experiment. Now, since then, we've done some amazingly accurate experiments, and it's not 6.67. I think in the book it's 6.673, blah, 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 blah. They've got it way out now. They know pretty precisely what the universal gravitational constant is. But hey, when Cavendish figured this out, he figured out you could use this to figure out the mass of the Earth. Okay, now let's do that. That'll be the last thing we do. Here's the Earth. Here's an object on the Earth that you're going to weigh. You know its mass. So we'll call it little m. This is big M. And we know the distance between the center of the mass and this object is just the radius of the Earth. And we weigh it. We figure out, we just take a spring scale and we measure the weight of this guy. And so we take the universal gravitational, the Newton's law of gravity. Force of gravity equals G m over, and this is the radius of the Earth squared. Okay, between the mass, our little mass here, and we measure this. So we know this, we know G, we know m, and we know the radius of the Earth. And we solve for the mass of the Earth is equal to force of gravity times the radius of the Earth squared divided by the little mass of our object. And when you do this, you get the mass of the Earth. Simple. And it turns out to be 5.98 times 10 to the 24 kilograms. You can try it. Figure out the weight of something and figure out what its mass is, and which you just take its weight and divide it by 9.8, and there's your mass, and you'll get this. It's very cool. And we can use Newton's law of gravity to figure out all kinds of wonderful things, and that's what we're going to be doing. We're going to be using it to figure out, later on we're going to use it to figure out how fast you need to go to be in orbit around a planet. We're going to figure out how to go up and never come back down. We're going to figure out how to escape from Earth's gravitational field. But that all comes later. So do the example problems. I would recommend you do the example problem now. I think there's only, there's a couple of examples to do, and then in class we'll finish up with the problems. And thanks for listening. See you in class.